created the first, what we should call true research and development laboratories. They conducted basic science and they conducted engineering application. Both were happening in the same place at the same time. Places like A.I. DuPont Institute created the Eastern Dynamite Company. I don't think I'd want to work with the Eastern Dynamite Company. Thomas Edison created Menlo Park Lab. At this point, scientists, engineers, and product managers were all working together. They were all striving to meet a very specific goal. So it was knowledge creation, but it was done in a very focused way. Each day, when the engineers or the scientists would finish their work, they would talk to their manager. And the manager was at a higher level, had a higher understanding of knowledge. And he would take the discussion with this person and this person, he would carry that knowledge and look for an opportunity to apply it. So it was the private sector that was really funding managed R&D. It was companies, because companies can't waste money. They have to get something beneficial out of it, or they go out of business. Remember, they don't have permanent jobs. They can go out of business this year or next year, so they have to deliver practical knowledge, but they also have to understand theory. And that's partly why Thomas Edison opened the Menlo Park Laboratory, because he was doing what we call cut and try experimentation. Let's combine this, let's make this larger. And he reached the limits of it and said, I can't do any more unless I understand more about the fundamental physics underlying electricity. So that's when he had to start doing more theoretical work. I just want to mention, I'm reading an excellent book called Creating the 20th Century. I've been reading this on my travels, and I only learned of this author because Bill Gates from Microsoft mentioned this author as one of his favorite authors, and he reads everything he writes when it is published. If it's good enough for Bill Gates, it's good enough for me. His name is Václav Smil. He's Czechoslovakian, and he delves deeply into the details, the historical details of technological development and evolution. And in this book, he argues, the title is Creating the 20th Century, because his argument is, and now that I read this, I'll revise my slide a little bit. His argument is that the technological developments that occurred between 1880 and 1910, roughly, 30 years, are the basis for everything we have today. The fundamental work in communications, automobiles, steel, fabrication, all occurred then. And since then we've had minor changes to it, but the fundamental principles and fundamental mechanics of everything we have in society really happened earlier than what we typically think. So it's an excellent book for teaching me certainly more about the details of why we should be looking at that period. This is another good book. I actually should travel to Brazil more often. I read this on my last trip here in October. I happened to be reading it when I was flying back and forth. And this individual wrote a book that's talked a little later than Václav's book. He's talking about the creation of yet another laboratory, the Bell Labs, and how the American government, U.S. government, allowed Bell Labs to have a monopoly over telecommunications. And that monopoly allowed Bell to have the money and the control over the technology. They didn't have to worry about other people taking the work and making profit. So they functioned more like a university, but they were functioned more like the Bell Labs were connected to Western Electric. So the university scientists and the laboratory engineers worked in the Bell Labs, and the managers would listen to what they were working on, and if they knew something, a new product, a telephone, a telegraph, air transmission of radio waves, if they knew there was something that was happening at Western Electric, they could take that knowledge over. Or they would take that person and say, you go work in Western Electric now until we develop this product. And in this book, they talk about great prototype inventions that were developed in the 1940s, 1950s, that sat until all the other infrastructure was ready, and the market was ready, society was ready. 1970s, 1980s, 2000, they were doing work with cellular telephones, the concepts and the prototypes of cellular telephones 40 years before they were introduced. They were doing so much early work with vacuum tubes that couldn't function in space, but once they came to the, they invented the transistor. I mean, everything that Bell Labs did. You can read this book, and you can, which I did. I was able to just simply diagram research, development, production, research, development, production, science, engineering, manufacturing. It's so clear. And this author is a New York Times author, so he did not write a technical book. He wrote a narrative, and he wrote the experience of the people who made up Bell Labs. The interesting point was, he said, at the time Bell Labs was created, the people they recruited for the laboratory were typically coming from small towns. They came from rural America because most of America was agricultural. And so the people they recruited knew how to install electricity in their home because it was new. They knew how to fix their tractor when it broke. So the people they recruited had very strong electrical, mechanical experience, and then they went to college. So by the time they had their PhDs and they came to Bell Labs, they not only knew great ideas, but they knew how things worked. So they were always thinking at both levels, the practical and theoretical. So this is, I'd recommend this for anyone who wants to understand more about the interchange between the three and more about evidence of how it works well. Then in the pre-1940s, there was new product developments. There people were in Bell Labs, but they could move and become university presidents, and then they move and they become advisors to government. So there was this free flow of individuals moving between the sectors, the economic sectors, and therefore moving between the methodologies. So there was no question that people understood the difference between science and engineering. There's no question they understood the requirements of manufacturing. So they could set those requirements to the scientists and engineers. So it was a very fruitful time, and that's why we see the documentation of the evidence of technological growth that occurred at that time. Now, it was the private sector that was funding this work. It was corporations and manufacturers that were doing it, because universities at the time were small. They were mostly private universities. They were funded by endowments from the wealthy and some tuition from students. But there were no large government grant programs at the time. So if you wanted money, you needed to go work with a company because companies had money. So it's so different in the past 80 years how things have turned. But this was when we had the success we had in terms of developing technology. So that the revolving door really helped people become experts across the fields, and that's why it's important to think about the three methods. Europe saw this happening in the US, so they did the very same thing. Germany created their own facility that would link science and engineering together, and it was very successful. The picture there's Albert Einstein and Max Planck, and there's a great picture of sort of the foundation of German science and engineering, working with companies like Siemens and Krupp and Zeiss. The United Kingdom, the British saw this happening, so they created something very similar in Britain. So everyone was sort of following the same model of contributing government resources to sponsor scientists to work in industry. So it was moving from industry support to government support because the projects were getting bigger and they were getting more risky. And industry doesn't like risk, so industry didn't want to fund less, and government started to move in to fund more. Then we had the World War II period. Germany began invading surrounding countries with superior technologies. And it probably partly come from people like Einstein and Planck working with government agencies. Ballistics, aeronautics, communications, guidance systems, incredibly sophisticated technologies. Why? Because they brought the scientists together with the engineers in support of the products from industry. So the U.S. and Germany, the U.S. and the Allied powers recognized we have to catch up. And there's this great quote, dependence, or when a man knows he is to be hanged in a fortnight, he concentrates his mind wonderfully. And the U.S. and the British and the Russians realized we were about to be hanged. There was very little that would be stopping Germany unless we raised our level of weapons to the level of the Germans. So the U.S. did the exact same thing. They took the scientists and engineers and put them together with companies and said, we need better airplanes, we need new radar, we need better ballistics, and that's what they did. So it focused the minds of the Allied leaders. They weren't concerned about who got the credit, who got the money. The point was to focus the effort on delivering advanced products and services, and that's exactly what they did. It's the clearest example we have of how aligning science, engineering, and industry together can have a huge impact on advancing technology. We just have not had a better example since. Maybe we have a few years. The U.S. National Defense Research Committee, they did mobilize all the sectors together to effectively compete with and even surpass the work of Germany. But some of that required us to get the German scientists, like Werner von Braun, for rocketry, in order to do more work, because Germany was still ahead of the rest of the world in terms of their conceptual scientific knowledge. The issue here is, when you look at the people who represented the committee, these were all either government people or they were academic scientists. And if you look at the name, it was the National Defense Research Committee. So again, where's the D? There's no research and development. Where's the engineering? So already we're seeing a change in the perception. The government people and the scientists start viewing all this as a research enterprise. But we start to shrink the D. It's smaller. The R gets bigger and the D gets smaller. Now, Vannevar Bush, who was part of these committees, he saw what happened in World War II and said, we can do this in other areas. We can improve our medicine. We can improve our commerce. We can improve all the other areas of our society just like we improved our military. So he published his book, The Endless Frontier. And he wanted everyone to focus efforts just like we did in World War II. But what happened instead? Different people had their own interests. There were already laboratories set up by the government. Vannevar Bush wanted to bring it all into one central laboratory. The Office of Naval Research had its own lab. The Army had its own lab. The National Institutes of Health had their own labs. They didn't want to combine. They wanted their own. So instead of focusing activities, it branched out. And I think that's where we took a detour from what would be considered a proper methodology. The special interests intervened. Each group said, I want my own. I want my own money. I want my own equipment. I want my own control. And so our U.S. Congress complied and basically allowed people to set up all kinds of different laboratories in all kinds of different circumstances. It's what we call pork barrel politics. The money is given to people because they ask for it. And because it does you good, you get votes. You trade money for votes. So we call it pork barrel. Pork barrel politics grew in science and technology. Each new government agency and program obtained more money and more staff. So government grew. The U.S. university system that was very small, very funded at a very low level, it said, we were responsible for all that wonderful activity. So you should give us money. Because the linear model of innovation said, give the money to science and wonderful things will happen later. And that's where we got the idea. So they become a conduit for the public money that's intended to benefit society. So academia grew. President Eisenhower, who was a general, then president in the U.S., said, be careful, the military-industrial complex will be too powerful for our democracy. He warned about that. But nobody paid attention, and defense industry grew. When you look at this chart, it gives you an idea. This is how much government funding grew in that period of a little over 1 century as a percentage of gross domestic product. Incredible growth. Now, can we argue that the benefits have followed the same trajectory? You can see, of course, you can see the large spike was World War II. Now, that was for a very specific reason. You can see how focused the mind was to catch up to the Germans and compete with technology. But it never went back to the original level, and it's only grown since. In the 20 years after World War II, no one questioned this growth because the economy was booming in the United States. And the United States was working with Europe and Asia to rebuild Germany and Japan and France. So there was a tremendous demand for manufacturing and industry. Then there was the Cold War between the US and Russia. Oh, we need better weapons. Oh, we need better missiles. Oh. And then the space race. Oh, now we need missiles that go not just to Russia, but now we need missiles that go into space and go to the moon. All of those accelerated the pace of technological growth, and we had in the US the money to do it because we were generating all the products and services for our society in a large portion of the rest of the world. So there were national and international markets. There was plenty of money. So there was no concern between the distinctions between scientific research and engineering development. Now, Eisenhower warned about the military-industrial complex. The one he missed was the bureaucratic academic complex. And I say that here knowing most of you are from the government or from academia. But the fact of the matter is the alignment of government programs and university grant activity is very similar to the military-industrial side. It's a closed market. The government collects money from the public through taxes, allocates it to a program for scientific research. That money goes out to the university, which gives it to its faculty who do the work. So there's no new net wealth being generated from that activity. And we have here Dr. Vannevar Bush, who wanted to do things differently, but he understood it wasn't going to happen. The President of the United States, and James Conant, who was the president at the time of Harvard University. Life became very good at Harvard. Their endowments, I should put a table in there. The amount of revenue going to Harvard and other Ivy League institutions just rose dramatically. They became powerful and they became influential, even more so than we were. However, by the 1960s, there was some clash of values. Military and industry was saying, we need more resources. Academia and government was saying, we need more resources. Now, all of that post-World War II growth and activity started to drop off. So the United States didn't have the money to just keep giving more money to everyone. So there's a really interesting, and I'm working on a paper on this activity. The Department of Defense, the U.S. Department of Defense said, we don't think it's all about science. We think engineering plays a large role in technological innovation. And they conducted a study called Project Hindsight. And they took 25 different weapons systems, military systems, armaments, artillery, radar, and they looked at generation 1 to generation 2, moving up to a new level of capability. They said, we will track the activity in science and engineering required to move from the first level to the second level of each of those products. And they did this, and they collected the data. It was very interesting. When you already have the knowledge you need, the vast majority of the effort is engineering, development. It's testing, it's experimentation. You don't need to go back to science anymore. You've learned and collected that science. They made the mistake before they published their final report. They wrote a little article, and they explained the results they were seeing. That article came out, and the U.S. National Science Foundation read the article. And it looked like this report was going to say, we need more funding for engineering, practical engineering, and less support for basic science. Before the final report from Project Hindsight could be released, the National Science Foundation recruited scientists. They had to make up a methodology. It wasn't even, it's not even well done. It's not even good science. They said, go pick 5 technologies, 5 products out there that you know depended heavily on basic science, and trace what happened. And that's why they called it traces. And they did a study in about 1 year. Lo and behold, science was most important. They published, and they even published their reports from traces before these guys from Project Hindsight could even get their paper out. So the National Science Foundation neutralized the evidence from defense. And both of these reports disappeared. There's maybe 3 paper copies, hard copies of Hindsight, and I know of 2 paper copies of traces in the United States. They're almost gone. So it's very political. very biased. This was not good science yet. It worked. It worked politically. It worked to influence the science, technology, innovation policy to say, oh yes, we must continue to put most of the money into basic science. So the solution, not only we should throw more money at the problem, spend more. So government kept spending more money on innovation, so even larger allocation to the academic sector, in some cases doubling the budgets over a short time. Yet no one conducted a study to see what difference it made. If you double the money, do you double the results? I know of one study that looked at the results. They doubled the money for programs in the United States and in Canada. And then 5 years later, they went and measured the number of publications. And here's the baseline of publications, the baseline of money. It doubled the money. How much do you think publications went up? 10. You know the study. In Canada, it was about 8%. In the United States, it was 3%. And they think the reason was because most of the people who get the money are already very busy. And maybe they can spend the money on more students or more instrumentation, but they can't do more than they do. And it turns out it's a very small segment of people who receive money that are productive in the sense of being able to publish. So those studies have disappeared. They don't like to talk, neither country likes to talk about those studies. But all of you from academia you know how the grant process works. If an agency has $1 million to spend, and they put out proposals, they put out a call, and people send in their proposals, and they fund proposals until the money's gone. Now the government says, here's another $1 million. We're giving you another $1 million. The agency says, are you giving me more people? No. Well, we can't. And will the money last? No. It's only 1 year, 3 years. Well, the agency can't expand because it's short term. So what do? They have to go back to the same program. They go, who did we not fund? We'll give them money. Or who did we fund? We'll give them more money. So there's not a one-to-one relationship between the dollars spent and the activity funded. But politicians don't know that. And the people who lobby for academia know the politicians don't know that. All they know is science is good. And we can't question what science does because that's not our business. So they've now been establishing metrics. So, okay, now we have to get serious about metrics. We better know what happens when we give more money. So they talk about government expenditures. Right? We're spending this much money this year. Spending $1 million, $110 million. And universities say, we've received $1 million, $10 million, $100 million. Those are inputs. That has nothing to do with the effect. That's only what comes in the front door. But we talk about those because we can measure those. So the level of sponsored research activity. That's the process. That's the activity that's happening. That's not impact. That's not outcome. The bibliometrics, how many papers were published, how many people cited those papers. Those are outputs, but they're not outcomes. They're not benefits for society. But these are the measures we have. So we're measuring what we can measure instead of measuring what we need to measure to understand the value of what we're spending. So no one really considered the long-term impact of doing these things. Everyone was happy with the system as it stood because, again, there was still enough money. So that's what we have now. To me, we have this muddled mess where everyone's confusing the terms, the methods. So now what we have, we still have the track 1 that I talked about earlier, grant-based scientific research. And we still have track 2. We have the contract R&D to produce weapons and nuclear plants and so on. Both of these programs still work very well. So they've continued along. I don't question either one of them. The problem is we now have a third track. We're talking about sponsored research and development, whatever that means. And people don't define it well anymore. For science and technology innovation, whatever that means. So now the idea is that we'll fund scientists and engineers in universities primarily that their outputs will be exploited by companies to produce goods and services. But those don't meet. The scholarly output for tenure does not meet the corporate requirements for profit. We no longer have the symmetry between the organizations. And these are the hybrid programs like the one that sponsors me. And I think it's possibly what could happen with your initiative, if you're not careful to make sure you balance this activity. Because the expectations of the systems and the attributes of the activity are not aligned, or they even conflict, they're incongruent. You can't get there from here, as we say in the United States. From where you start, you can't get to where you want to end because you don't have the alignment between the methods, the training, the people. And those hybrid programs are saying, oh, we need better products for people with disabilities. So we're going to give money to universities. But we're talking about products and services. So are these programs saying that academics are better equipped than industry to deliver good value for money? Are they saying that tenured and career employees should dictate the rules of innovation for the private sector? Are we saying that corporations they don't have ideas anymore? So companies are saying, we don't know what to do. Is that really what we're saying? Companies have more opportunities in the back room than they could possibly afford to do. They don't have the money. It's not like they need someone else to tell them how to do their business. But we are essentially saying, in order to improve products and services, we're going to give the money to universities. This is what we're saying. We're saying, and in the United States, we have a lot of student design programs, student invention programs, especially in areas like assistive technology. So we're saying that students and small companies really know what society needs. It's just not true. None of these premises are true. Yet no one challenges this. So why are we trying to improve industry yet we're giving the money to, giving public money to government agencies, to universities? Say, well, where's the technology transfer? Well, how can there possibly be transfer when nothing is allowed? We have a lot of these hybrid programs in the United States. We have the National Science Foundation, National Institutes of Health, the National Institutes for Standards and Technology, Department of Education. We have many of these programs, and none of them are working very well. Canada, their NSERC program probably works best, but it's still struggling. The Canadian Institutes for Health Research, they're doing good work in conceptual science, but they're really struggling with products and services. They're having the same problem in the US. The European Union, same problem. A hybrid program, the methods and the expectations and the incentives are not aligned. 35 years they've been funding activity in the area of assistive technology, and they're still saying, where are the new products and services? We have lots of papers, but we don't have products. So my question is, which direction will the CNRTA go? Will it follow this model? If it follows this model, it will follow the results, certainly. What we're talking about is these false dichotomies and erroneous contractions where people talk about the push versus the pull. They talk about R&D, they mix the two, there's one term. S&T, science and technology. Science is a method. Technology is an output from a different method. Yet we call it S&T. Where do these, this is the muddled mess I'm talking about. How can you define your intentions through policy if you're not even using the correct terms in the correct way so that everyone is aligned to do the work necessary? People confuse discovery, insight, invention, innovation. I've tried to show you that you can use them distinctly for different types of knowledge state. The scholarly versus societal outputs and outcomes and impacts are different. Society expects one thing, and government's funding something else. The expenditures in bibliometrics are not the real measure, which is new net wealth. You need to generate something that brings new net wealth in order to have an economic impact. So they're counting what is countable rather than counting what matters to society. And then look at Are any of you involved in economic policy, science and technology policy, measures of innovation? There's these international agreement on how to measure a country's level of innovation. And they say the percentage of money expended on research and development as a portion of gross domestic product is the measure of innovation. But they're not distinguishing between R and D. So my argument to the people who make this point is saying one country spends $1 million, spends 2% of its gross domestic product on R&D, but they spend all of it on basic science. This country also spends 2% of their GDP on R&D, but they spend all of it on engineering. A third country spends nothing on R&D, but spends that 2% on bringing new products and services to the market. How can anyone say that those are the same? They are by mixing the two, you're muddling and losing the detail. Now, of course, academia, universities like to mix the two because they can claim that research drives the process. Industry is no better. They're not innocent here. Industry, if they can claim a higher percentage of their expenditures are R&D, it has a preferential tax treatment. They pay less tax on the money spent on R&D than on the money they spend on actually generating the products, the cost of products. So everyone's quite happy with this set of terms, but they're ignoring key factors and they're completely missing the causal links between things. No wonder we keep spending money and we're not seeing the results that we think we should be seeing from it. Even one of the newest government models in the United States, this is their chart of innovation. They have research that generates knowledge. I guess there's only one type of knowledge. Knowledge, they call it. It's published, and then that generates new ideas for more research. Well, some of it leaks out into invention. How did it go from knowledge to invention? There's no method shown there. After invention, they have development. Well, no, that's production. So even our National Institutes of Health are continuing to confuse and misalign these terms, and yet they want to sponsor programs for innovation. So I go back to this chart I showed you at the beginning. To me, this is why we have this result. After 40 years of spending, this agency spends about $100 million US per year on R&D to benefit people with disabilities. So I asked the agency, tell me how those first two columns of publications and presentations, explain to me how they benefit. Give me one, take one paper and explain to me how it becomes a benefit to a person with disability. It's a very difficult challenge, yet you continue to fund the same combination of activities. Why do they persist? We shifted power and influence from one group to another after the 1940s, from the corporate sector that was focused on delivering products and services to the not-for-profit sectors, government and universities. We distorted Vannevar Bush intention to replicate the success of World War II in other areas. So now we have both a military-industrial and an academic bureaucratic complex. We have two complexes on the shoulders of the taxpayers of our societies. And we have this perpetuation of these false paradigms of what innovation really is and what technology transfer is. And we all accept this, what we call aspirational language. A new discovery that someday may lead to. A new discovery that may hold the key to improving, ... It's always about in the future. And we accept that as a state of activity. But what we have to do is restore parity. We have to clarify this muddlement. Right? We have to simply establish terms, definitions, and proofs. It's basic scholarship. We need to return to basic scholarship. The challenge is, what do you mean when you use this word? What is the context of using that word? Are you defining that word the same way I am? And they may challenge you back and say, well, why should I accept your definition and use of the word? You say, here's my proof. So we need terms clarified, definitions established, and proofs performed. And these are essential to any policy yet. I don't see them in STI policy anywhere. We have to acknowledge that there's different states of knowledge and there's transitions between those states. That's the transfer. Between conceptual discovery and invention, you have a translation of knowledge. Between the invention and the product, you have a transfer of technology ownership. And then from the product to the marketplace, you have a commercial transaction. We're not even talking about the first one and the third one. It's some black box is the tech transfer. But they're very specific types of communicating and adopting knowledge that moves knowledge from one state to another. And so we have to apply. We have to ensure the models, the methods, and the metrics are all congruent across these activities. If you don't, it's rhetoric. It's not good science. It's not good policy. It's not good common sense. Now we have to hold the scholars accountable to say, enough with the rhetoric. Where's your demonstration of the reality? Where's your replication of the activity? Where's your skepticism? You say, oh, fun science and good things will happen. Shouldn't someone question that and say, well, let's look for proof. All we have today is anecdotes. We have a handful of anecdotes that are constantly churned to say, this is why we have to fund all the science, especially for the hybrid program. But it's not necessarily true. Innovation and impact. Traditionally, each sector defines it their own way. But we're seeing a change. Finally, the U.S. National Science Board in 2012 defined innovation in the context of the commercial marketplace. And that's only after OECD in Europe did the same thing in 2005. So we're beginning to see a change in definition of limiting the term technological innovation to products and services in the marketplace and the processes that support them. So it's an encouraging sign. Because innovation impact implies utility, the value I discussed earlier. There's three expectations when you say government is going to fund activity to benefit society. We think it's new or improved products or services with some economies of scale to make them feasible for a company to sell and contribute to quality of life. We think it means there's sufficient return on the investment so that the company can keep making that product. Otherwise, it won't do anyone any good. And in turn, they will generate new net wealth that is partially collected by the government to fund new activity. That's the way we want to see the system work. And the public, when you say you're going to benefit society, they're not thinking someday. They're thinking 5 to 10 years. They want to see something in a shorter time frame than we're typically thinking. So innovation's context should be social impact in the commercial marketplace. When we talk about funding activity to generate technological innovation to benefit anyone, it should be in this context. Otherwise, we're starting to mix the terms and mix the methodologies. Because the commercial marketplace is the path to utility. Industry only survives because it delivers products in the competitive marketplace. That means money to the seller and function to buyer. If there's no sale, if research discoveries are freely disseminated, that doesn't generate new net wealth. Granted, it builds the base of knowledge, that's fine, but again, that's track one. You can't confuse track one with this hybrid system. Research and development outputs do not equal market innovations. So it's important to untangle the term because each method has its own rigor and its own jargon. It has its own terminology, so we all need to understand what each other is saying and what the requirements are of the methods. The actors involved between the scientists, the engineers, the manufacturers, the government people, each of us is typically trained in our one method. And so we put the most confidence and value in that method. And we don't know what these other people do, but maybe it's okay. So we need to understand and appreciate that all the methods have value and rigor. And right now, academia and government dominate STI policy. We really do not have industry at the table. There's a bias against public money going to industry, but it goes to universities, and they benefit. Why can't we look at a different model in these hybrid programs of saying, okay, the market is failing, so therefore the government must directly fund industry, and industry can decide which scientists they need to talk to, which engineers whose work is relevant they need to pull in. It's much more like the prize approach, where the prize is put out. We will give the prize to the first private rocket in space. We will give the prize to clean up an oil spill. So the prize method doesn't try to dictate the process, it pays for results. So that's a different approach to these hybrid programs. And we have to stop debating which one's better, which one's more important, which one's more. They're all interdependent. The books I mentioned clearly show the historical record that we need all the groups, all the sectors, all the methods working together in order to advance technological innovation. At the end of all this, I can take pretty much all the words that I used in the context of the seminar here today and show how easily they can be aligned. We don't have to have confusion and debate. We can easily clarify when we're talking about Aristotle's episteme from 2,000 years ago. We can talk about what that means in terms of set of terms. And we can match those terms when we talk about techno, we talk about engineering. And again, we have parallel terms when we talk about industrial production. And we can talk about the states of knowledge being differently discovery, invention, and innovation. And they align very easily. Legally, they're aligned. Methodologically, they're aligned. So part of my work, I still work directly in the field of assistive technology, but when we're talking about the models, the methods, and the metrics, when I learned that there were many programs that are this hybrid type, struggling to be successful, I'm spending more of my time talking at this level of conceptual structure as opposed to the specific area of assistive technology. Tomorrow at Tech, I'll be talking about a stage gate model that aligns all these activities and applies the best practices from industry with the best knowledge from academia to collectively generate what we hope would be commercial innovations. So basically, to conclude, the way forward is to integrate the conceptual but differentiate the operational. We want to make sure we understand conceptually how the three methods work and how their outputs are integrated. But operationally, we can't confuse scientific research with engineering development. And we can't expect that those two can substitute for industrial production. We have to consider the three distinct states, know the role of each of the states in the process, and we have to plan and budget accordingly. If there's a program that is attempting to generate beneficial technological innovations, and all the money is going to one method or one activity, the probability of success is lower. So we have to look for the plan and the budget to be aligned across that. And engaging industry early is key, because most of the publications that talk about new product development, most of the publications are at the early stage. It's all about getting the early stage right. And the journey of 1,000 miles begins with one step. And they say the first step is an important one. Getting that right increases the probability of success. Getting it wrong dramatically reduces success. And it shouldn't be unreasonable to ask government people and university faculty to apply evidence-based frameworks. This shouldn't be something we make up as we go. We should use structured methods. So we link the three methods, communicate knowledge in the three states, and integrate all of the stakeholders involved. That's government, academia, industry, clinicians, consumers, and what we call brokers. That could be legal attorneys, it could be educators in schools, it could be employers out in the market sector. They all have a stake and they all have a role. And unless we're integrating all the stakeholders, any one of them can cause the project to fail. So tomorrow I'll talk about, at Reatech, I'll talk about this need-to-knowledge model, but that's on our website. All the material is freely available. I publish in open access journals. We are hoping soon to take our papers, because they're open access, we can now take them and make translated copies and post them freely on our website. So we're hoping to increase communication by doing that. Here's a few of the publications. Like I say, they're mostly in open access form. This is just a short bibliography. I think you'll have a copy of the slides that anyone who wants a copy could just ask, or you could send it out to the people who attend. And even though I'm a critical friend, I'm very respectful of the agency that funds my work, but I'm critical about some of the things we do. So I try to be a critical friend, but I always try to acknowledge the U.S. Department of Education that funds the work that I do. And at this point, I thank you for your attention, and I hope you find it useful, and I would be very happy to have an open discussion with any of you who care to raise a question or challenge me on any of these points, because that's how we'll increase our understanding. So, abordado.
Pessoal, está aberto para perguntas, pode levar o microfone.
Good morning, everyone. My name is Joe Kamanda. I'm working at CTI on software development technology. I would like to restrict the first part of your talk. I think the big challenge is how to conciliate the difference among different languages, among different stakeholders, to translate or to transform speech terms from one context or model to another. Do you agree?
Yes, I certainly agree. And I think the reason I talk about values and I talk about personal interest and incentives is because we have to recognize that those exist. Because Upton Sinclair, he was an American author who wrote about the meatpacking industry in the early 20th century in America, in the U.S., and the problems with the meatpacking industry. But he has a great quote, and I didn't include it here, but he said, there's nothing more difficult than to explain something to someone when it is in their best interest not to understand you. And that's where we have to recognize the interests of the people we're speaking with. And we have to recognize that I will not get a government agency to change its approach unless I can appeal to their interests and their values. And so that's my continuing dialogue with my own agency, recognizing our goal, our mission, is to improve the quality of life for people with disabilities. Yet, as an agency, your focus is on scientific scholarship. Recognizing the value of scientific scholarship, how do we meet the requirements of our target population? So one of the changes now is the agency head, who's appointed by the U.S. President, is now a person with a disability. So we get more of an advocacy from a person who understands the practical application of the science, as opposed to a director who's very prestigious as an academic. So we need the right people speaking and listening with a shared intent to accomplish the same goal. But in the meantime, we have to recognize the goals, the short-term goals that influence all of our behavior.
I have another. Then one possibility could be to negotiate some standard jargon to to understand, could be understood by several stakeholders. And I think it could be to force academy to publish according to this standard jargon, yeah, like the innovation terms.
In fact, last year, I submitted a proposal to the National Science Foundation. They have a fairly new program called the Science of Science and Innovation Policy. It's perfect. We wanted to make this a science. We want to understand it. So I proposed exactly what this is. I proposed a project that would define, that would set the terms, establish the definitions, and provide the proofs. And it was rejected by the reviewers. Absolutely. I won't use the term that I could use to describe what they did to my proposal. One of the reviewers actually said, I can't believe you would put this in writing. He said, I for one marvel at the diversity of our language and how wonderful it is that we can speak about the same activity in so many ways. I was just dumbfounded. I do plan to pursue that funding, but I think until we establish the foundation, it's first principles in engineering, right? Unless you have your first principles, how can you possibly build a structure? So until we set, you know, the terms, the definitions, and the proofs for each of these, I can always have a different opinion. I was at my sponsor recently, and they said, we have an expert from the information technology field who works in cloud-based computing. And we asked him about your model, the stage gate model. And you know, a stage gate, people are incorrectly assuming that it means it's systematic and directional. It doesn't have to follow one after another. It just means these are all the activities that must occur in order to maximize the probability of success. But people think because it's in a sequence that it must happen in a sequence. It doesn't. But they said, this person who came in, he doesn't believe